Hey everyone, welcome back to another video with Cam Room 5. In today's video, we're going to continue the rate of reactions and we're going to see how rates and the graphical analysis of rate of reaction is connected. Because graph is how a lot of questions from this chapter are coming in the examination. So we talk about the time versus mass graph and the time versus volume of a gas graph. Each graph has two main components. First is the height of the graph, which means to what value of the y-axis the graph reaches. And second is the gradient or the slope of the graph. So gradient or slope is another thing and the y component is another thing. The height of the graph shows us what is the amount of product received, which is related to the amount of reactants. So it shows how much product has been made, which is obviously dependent on how much reactant was used. The gradient shows the speed of reaction. So a steep graph or not a very steep graph shows how the rate of reaction is happening. So when we talk about these two components, let's take an example. Let's have magnesium carbonate, which is solid in nature, reacting with aqueous hydrochloric acid to produce magnesium chloride, carbon dioxide gas, and water. Imagine we have a graph where we have the time on the x-axis and the volume of the carbon dioxide gas in unit of centimeter cube on the y-axis. We have excess of magnesium carbonate in both cases, but every time we have acid as limiting reactant, which means the reaction depends on the concentration and the amount of acid. Imagine we are taking 10 centimeter cube of 1 mole per decimeter cube acid. This is the concentration and volume. And when we did our calculation, imagine, for example, we got this kind of graph, which shows us that 240 centimeter cube of carbon dioxide gas was collected and the reaction almost reached a constant horizontal line at 50 minutes. So it produced almost 240 centimeter cube of the gas in 50 minutes. And at 50 minutes, the volume stopped increasing, which means the reaction was completed at the 50th minute. You can see the gradient is really high in the beginning and then it becomes lower. And then at the horizontal line, the gradient is 0. Let's have another experiment with the green pan where we have excess of magnesium carbonate again. Again, the acid is the limiting reactant, so we have limiting reactant as acid. This time, we are taking different amount of the acid. This time, we are taking 5 centimeter cube of, again, 1 mole per decimeter cube acid. The concentrations are same, but the volume is lesser, which means less moles of acid are used over here. And since less moles of acid are used over here, the amount of product would also be lesser. So the graph wouldn't reach the same height. You would not get the same amount of volume of carbon dioxide because you're not using the same amount of acid. Excess reactant we don't consider, right? So everything depended on the amount of acid. The reaction almost got completed in 37.5 minutes, and this time you got half the volume of carbon dioxide gas because you were using half the volume of the acid. So the amount of the reactants decide what should be the amount of product received, which is the Y component. You get more product if you use more reactants, you get less product if you get less reactants in the beginning. So more volume of carbon dioxide was produced if you used more moles of acid, and less moles of the carbon dioxide were produced if you used less moles of the acid. The rate of reaction depends on the gradient of the graph. Imagine we have a similar graph from the last time. Again, the excess of magnesium carbonate was here. Let's have the same thing. For example, 10 centimeter cube of 1 mole per decimeter cube acid is same thing over here. And that's the limiting reactant. But imagine that this time we are running an experiment. Let's label it first. 50 minutes were required to produce 240 centimeter cube of the gas. But now we are repeating the experiment with a different set of conditions. For example, in experiment 2, we are using again excess of magnesium carbonate, but this time I am using 5 centimeter cube of 2 mole per decimeter cube. This is the concentration of acid. Now, I not only decreased the volume of the acid, but I doubled the concentration. Since the concentration is doubled, the moles are same as experiment 1. So the height would be same, but this time the moles are the same. You should know this. 10 and 1, 5 and 2. They give the same moles on both cases, but the concentration is higher in experiment number 2. So even though the height of the graph should be same, we'll see another different over here. The height of the graph would be same on both cases, but you would see that the graph number 2, the experiment number 2 is steeper. Why is it steeper? Because this time you are using more concentrated acid. So the reaction almost got completed in 25 minutes, half the time. Because concentrated acids help in faster reactions. So even though you have the same moles, but higher concentration results in faster reaction. You can notice the gradient of the purple graph is more than the gradient of the blue graph. So you can say that gradient of graph, the purple one, is more than the gradient of the blue graph. G is equals to gradient, and gradient shows that the rate of reaction in experiment 2 was faster. Let's have a practice of graphical analysis questions. So imagine for example, I'm running an experiment between, let's say, barium carbonate and hydrochloric acid. I have 4 experiments. Every time barium carbonate was in excess, I have 10 centimeter cube of 1 mole per decimeter cube, 20 of 0.5, 10 of 2, and then 10 of 0.5 mole per decimeter cube. The volumes and the concentrations of the acid are given. Let's calculate the moles of the acid, which is the limiting reactant. I don't want to calculate the exact moles, but you should know that CV divided by 1000 is a formula that I've taught you earlier. So using the CV, it should be 10 times 1 divided by 1000, which means 10 over 1000 moles. The second is again 10 over 1000 moles because 20.5 is 10. The third experiment gives you 20 over 1000 moles, and the fourth experiment, D, gives you 5 over 1000 moles. The number of moles of acid are same in experiment A and B, which means the height should be same. There are more moles in experiment C, which means the height should be more, and there are least moles in experiment D, which means the height should be lowest. Another thing I want you to notice is the concentrations. The concentration is highest for experiment C, which means C should be the fastest and the highest. A and B should be the same height, but A and B would be same height, but A is slower and B is even more slower because B has even more dilution over there. While experiment D is again very slow experiment. Imagine we have a graph and we have multiple curves received. The purple one, the sky blue one, the orange one, and let's say the pink one. You can notice that there are 2 graphs with the same height, the purple and the pink one. The height of purple is equal to the height of the pink one. They are producing the same volume of carbon dioxide gas from the y-axis, which means they have the same amount of reactant used. So A and B are the pink and the purple one. I don't know which one is which, but you can notice that A has a higher concentration of acid, so A should be steeper. Purple has less concentrated acid, so B has lesser gradient. B is a little slower. We can also notice that the moles were the highest in experiment C, so the sky blue graph would be experiment C, because it is giving you a very high volume of carbon dioxide. So the blue graph represents experiment C, because the most moles of the reactant were used. High moles of the reactant give you more moles of the product. The experiment D is the orange one, because it has the least moles of the acid, so the graph is the lowest. It gives you the least volume of carbon dioxide. And you can also notice that the concentration of the acid was very low, so the graph is not very steep. The orange graph does not have a very high gradient. So we can see that the gradient helps us understanding the rate of reaction, the fast or the slow idea, and then the amount of acid or the moles of the reactant help us understand the height of the graph. In coming video, we'll try more experiments and more graphical analysis from past paper questions. Stay tuned, guys. Thanks.